Hi, in this video we'll talk about randomness on the blockchain, so random numbers and blockchains. This is going to be an explainer video, so purely theoretical, but it's going to be very approachable to people who aren't really into blockchain or aren't very technical. So, randomness, or the importance and impossibility of random numbers in blockchains. Why do we need random numbers? Well, when you have a blockchain that does proof of work, where everybody has the same amount of influence because they're mining and everybody's using the same machines, and the more machine power you put into the proof of work, the more chances you have of winning the block reward, that's kind of taken care of. You don't need any randomness inherent to the protocol to make it work. But in the advanced systems like Ethereum or Polkadot, where we actually have proof of stake, and proof of stake implies that people will stake a part of their coins into the system to guarantee that they'll be doing good work. You need a way to select randomly the people who are doing that work so they can be adequately rewarded for it. But again, you need strong randomness because you don't want somebody to manipulate that selection and own all the slots. So, this is an example of a distribution. Let's say the people are the stakers, the participants in the system, and the chains are blockchains or shards in Ethereum. Now, we need a way to distribute this randomly so that we can't predict who's going to be processing each chain or each shard, and so that we have a distribution that is adequately fair and random, and so that some people cannot block others from doing their job. For example, our randomness has selected the top two people to validate on the leftmost chain. The other two people are validating the rightmost chain, one person is validating the upper chain, and one person is currently without a chain to work on. So the problem with randomness in computers is that computers are deterministic. 2 plus 2 will always equal 4 in computers. If it doesn't, then the computer is not very good. A computer must produce the same output for the same input every time. Otherwise, they would fail at their basic mission, which is computing. So, a random number by a computer is actually pseudo-random. And I say pseudo because the computer, if it gets the same input, it's always going to produce the same output, but the input can be reasonably random. And this input is what we call a seed. So, you have a seed with which you seed this function for computing randomness. And that seed can be anything. It can be the number of steps you took today. It can be the number of bananas you ate in the last month. It can be the number of cars that passed on the road next to you this morning. But it can also be esoteric stuff, like, for example, atmospheric noise. The website random.org, which is currently the most random publicly available number generator, uses scanned atmospheric noise to actually produce random numbers. And this is as unpredictable as it gets. Another example is mouse movements. This is a popular website from ages ago, which is no longer in use really, where you can generate a Bitcoin address for yourself, a Bitcoin wallet, by moving your mouse on the screen, moving your mouse cursor around the screen, and this movement collects this randomness. For example, let me show you. So I'm moving my mouse, and it's collecting, and you can see these numbers change. This is the seed, and as it reaches 100%, boom, I have a private key and a public key, which is the address of the Bitcoin wallet. So, now, if somebody could repeat my movements exactly, they would get the exact same wallet. But given the resolution of my screen and my erratic movements and the fact that I'm walking while I'm moving it, there's no way to predict my movements and to repeat them accurately. So, this is kind of reasonably random user input. There's also other approaches. For example, there's a paper published in 2018 on using ECG, so heart rate variance, to generate such randomness as well. And when you scan someone's heart rate, it's always going to be, there's always going to be some variance between the beats that you can actually use as a seed. You can't really hear that variance, but you can detect it if you use very precise measurements. Nobody uses this, but it's a fun proof of concept. And a final example is lava lamps. So this is actually news today by the leading CDN provider in the world, which is Cloudflare. And Cloudflare is a service which sits in front of many websites and basically protects the website from traffic. So if the website gets an influx of a lot of attack traffic, of spam traffic, then the CDN will block it. And it also serves as a means to distribute your content globally, so that if someone from China is accessing your website, it doesn't take forever to load because it's accessing the server in the US, but instead it is copied to China. So a server in China is accessed from China. Now, Cloudflare uses these lava lamps, and lava lamps are the lamps where you have this ball of wax inside, which when it heats up, it melts and it floats to the top. Then as it cools down, it falls down again, and so on and so forth. And because there are so many of them, each image, each snapshot you take of them is a different layout of pixels. And this is their source of randomness. So they feed these images into their system to generate the private key for encrypting this internet traffic. This is called LavaRand in their implementation, and it works fairly well. They still use this in production today. So computers are pseudo-random, or reasonably random, given enough of a random input. But this is not good for blockchain. Why? Because there's no mouse cursor chain to feed people's mouse cursor movements into the blockchain. There's no ECG chain to feed people's heart rates in there. There's no lava chain. There's no weather chain. There's no way to get this data into the blockchain reliably and regularly. So we also have this so-called oracle problem. When you need to put external data, so data from the real world, into the blockchain, that's called an oracle problem. Because we call the service that inserts the data into the blockchain, we call that an oracle. And an oracle will usually submit a transaction into the blockchain, store that data in there, and then all of the other contracts on the blockchain can read that data. However, because it's external data, the data can vary from location to location. A very typical example is weather data. So, if I have a weather station outside and it's raining, my weather station will say it's raining. But someone at the same time might have a weather station in Argentina and it's sunny there. So whose weather station is right? Whose value is inserted into the blockchain? Now, this is just two values. Imagine if you had an oracle for something more complex. So imagine if you had an oracle for lava lamps. So if I have a wall of lava lamps and someone else has a wall of lava lamps, then we have completely different values. And if many people have this as well, then we have basically hundreds of forks in the blockchain happening at the same time. Because if two computers participating in a blockchain network get different data, then they cannot build the same chain. And at that point, the chain forks. And you have a problem because the nodes disagree. Somebody's wrong, somebody's right. So the oracle problem is a serious issue in blockchain randomness and cannot help with that. So how can we get a random number inside the blockchain? Well, remember how blocks are produced. If you're not familiar with a hash is basically just a long list of letters and numbers. And essentially that translates to a big number. And a hash is always the same length. So it always contains the same amount of characters, regardless of the input into the system. Now, if you put in a tiny bit of information, or if you put in the entire phone book, it's always going to produce the same length of data. But you can never predict what it is. And I'll show you this. So this is a SHA-256 generator. And say, for example, that this white block here, where I can insert some data, is in fact a block in the blockchain. So this white block is a block in the blockchain, and the block in the blockchain can contain transactions. For example, Alice to Bob, 5 Bitcoin. Bob to Charlie, 3 Bitcoin. Now, you see, as I type this, the hash of the block is changing all the time, because this hash is being computed from all the information in this white box. So, as soon as I enter a single character more, you'll notice that the hash changes completely. Nothing in common with the last one. So completely unpredictable. Even if you know what data is going into the block, you have to calculate it to even assume that to know what value you'll get. So now in Bitcoin, when miners do their job, what they do is they adhere to a programmatic rule where they said, if the hash of a block starts with a certain number of zeros, then that block is valid. And what does that mean in practice? Well, that means that these miners are constantly guessing some nonce that they add to a block until they get enough zeros at the front. Let's assume that we want 2 zeros at the front of our hash. I can keep typing. Boom. There we go. We have 2 zeros at the front of our hash. We guessed it in 10 seconds. And this hash is considered valid. So if I'm a miner, I'm going to send this to the network. I'm going to tell everybody else who I'm connected to, hey guys, these are the transactions I'm processing, Alice to Bob, Bob to Charlie, and my nonce is this string, so this nonsense of data. Put it into your hashing function and check if I'm right. Everybody else is going to say, all right, let's check. And they're just going to, if they have nothing, paste my data in there. Sure enough, they get the 2-0 hash. And then they'll see that I'm right and that my block is valid. I get rewarded from the blockchain, I get the free bitcoins, and everybody else builds on top of my block. They say, all right, you were right, let's keep guessing. Let's get some more transactions in there, let's build more blocks. And this is how hashing works in this case. And notice that since it's so unpredictable, you can't know what the hash is going to look like. So the final 2 numbers, for example, in this case A and B, would be also unpredictable. So why not use that as a source of randomness, right? Like every block that gets produced is reasonably random. So you can actually take that as your seed. And sure, that works. That's actually in use. Some raffles, lotteries, quizzes and so on, they will use this method. But it's not good enough. The problem here is payout versus block reward. And how that works is, if your block reward is smaller than the potential to gain money from cheating and producing a block that is favorable to you, or a hash that is favorable to you, then of course you're going to produce a hash that is favorable to you. For example, if you have a lottery, and actually, let's keep it even simpler. Let's say you have a coin flip, and that coin flip depends on whether or not the last character in a block hash is odd or even. So, if you have a coin flip, which rewards you, for example, 20 Bitcoin if you win, if you call it heads and heads comes up, then you're obviously more incentivized to keep calculating that hash until you reach the solution that will give you 20 Bitcoin, rather than submit the first valid block you find, which will only give you 12 Bitcoin as a reward for processing the block. So that's something to keep in mind. Now, what else can we use though? So Ethereum came up with this solution called the RANDAO. And DAO stands for Decentralized Autonomous Organization, and RAN is for random. So, a very layman's overview of how that works is, imagine a bunch of people in a room, and everybody imagines some sort of number in their head. And then we decide the following. The resulting random number is the result of the mathematical equation that goes like this. Everybody reveals their number one by one. We take the square root of each revealed number, we sum those together, and then the square of that sum is our result. Simple. So we go, you there, what's your number? 10. You there, what's your number? 4. Alright, so we know it's 3 point something plus 2, and so on and so on. Now, this is also reasonably random, because you can't predict who's going to have which number in their head. But there's one bit of influence. The last person to reveal their number has one choice, which is to reveal their number or not. They just pretend they're not there. And if they have a kind of horse in that race, if they can win by influencing this by one bit, if they can on the fly calculate that with their reveal the number is going to be X, and without it it's going to be Y, and they like X more or Y more, they have that one little bit of influence. Now, given that the number of participants in this system is vast, it's hundreds of thousands of validators doing the same thing, it would have to be some fairly enormous, unimaginably enormous server farm to calculate that in time to get an advantage, and also the reward for that would have to be extremely immense. And even if you do that, it would only be valid for one block. It's not really a risk. Still, they're trying to mitigate it. How do we mitigate the one bit of influence in Random? With VDF. VDF is a verifiable delay function. That's just fancy speak for saying it's predictably long. It takes a predictably long time. It also means that it cannot be parallelized. In other words, you can't throw more computers at it, because even if you have 20 computers processing that problem, it still has absolutely no effect. And why is that possible? Because you have something like this. So, if you take a number and you keep squaring it, you end up with a truly enormous number. And to get to the next step in that equation, you basically need to have calculated the previous one. So there's no way to start from a higher level and then keep going, because you had to get to this one somehow first. So more computers are not going to help here. Only stronger computers will. And there's a website, vdfresearch.org, where a whole new branch of research has sprung out around this, with many blockchains collaborating. A lot of funds are being thrown at this, and the result will actually be a small box, not unlike a Raspberry Pi, which you will plug into your wall, and that's going to be doing the calculation in the best and most power efficient way possible. So this is going to be open source hardware. It's going to be mostly freely distributed, and anybody's going to be able to plug it in and run it. And running just one will help multiple blockchains. Just one is enough for the entire system to survive, because you can't really outdo that one. If it succeeds in its mission and sends it to the blockchain, we have a VDF result. In order to actually beat it and get ahead of it and regain that one bit of influence back, you would have to create a 100 times more efficient device to do that same thing. Financially unviable. So VDF is a very secure addition to the RANDAO, because it puts the RANDAO number into the VDF, and then the RANDAO number is essentially delayed. It is delayed by 1 hour, which will make sure that the conspirators' effect is also delayed. So their window of opportunity will be long gone by the time they get to the point where they can influence something. So VDF will kind of remove that one bit of influence. And as such, it's apocalypse ready. So keeping just one of them alive will keep the entire system alive. Now, in Polkadot, a different system is used. A system called verifiable random function. And how that works is every slot, and slots are discrete units of time, 6 seconds currently, but may or may not change depending on network performance. And in every slot, all validators execute the VRF function. Now, the VRF function is local. It's local to that validator. So the validator doesn't execute it on chain. It executes it for itself only. And they do this, they check if they're the validator who can propose a block on the relay chain. How do they check this? We'll get to that. But essentially, if they find out that they are, they try to propose a block, a new block. If they're not, they just wait it out. If they tried, others will check the proof of their random roll. So, in pseudocode, you can imagine it like this. The direct result of the VRF function, which takes as its input a secret key and some randomness, will always be the result of the random roll and proof that the roll was achieved. What's the secret key? The secret key is a cryptographic primitive which all validators have and periodically regenerate. So you have this secret key, like a secret wallet, that is used only for generating these random numbers. Only for that. And discarded when it's used. And the randomness input we'll explain a little later. So, then you get the result and you get the proof. If this result is less than a certain number, a threshold, set in the protocol, so it's just a configuration setting, then the validator is okay to try and propose a block. Otherwise, the validator just skips it, waits it out. So, what's the randomness input? The randomness input is the randomness of the previous two epochs. And epochs are collections of slots in 4 to 6 hours of length. So, a discrete unit of time that has passed on the blockchain, the randomness that was achieved in that unit of time is actually the seed in the new calculation. So randomness of one block affects the randomness of the next, and the next, and the next. And the proof that we mentioned is kind of like you need to prove that you got a result, but you don't have to prove how you got it. In a very trivial example, imagine a die with different colored sides for the various numbers. If you rolled it, and if you got a 5, you would submit to the network 5 blue. And then everybody would get that result, and they would see, okay, Bruno got 5. How do we prove that? Blue is, 5 is blue on my die. Is 5 blue on his result? Yes, it is. Okay, that's proof enough. So, in a way, much more complicated, but in a way this is how it works. You prove that you got a number without proving anything else. And if that matches, then you're a valid block producer for that slot. So summing up, randomness in computers is impossible. True randomness. Randomness from external information has an oracle problem. It's bad for blockchains. You can't really put external info into the blockchain. And randomness of blockchains is deterministic, so it has to be the same on all the nodes in the system, otherwise forks happen, but has to be unpredictable because we need to fairly distribute the workload between the validators and the rewards. So we do this via Random and VDF, or VRF. That's all I have for today. If you have any questions, please put them in the comments. Remember to like and subscribe if you like this video, and I'll talk to you in the next one. Cheers!